So equilibrium. So we know that something is equal here. It starts with the word equal. And what we're going to be focusing on is equal rates. Okay. It's very, very crucial that you know what it is that's equal. When we talk about equilibrium, we're discussing equal rate. Okay. How much product is being produced? How much reactant is being produced? So what I mean by that is some physical and chemical reactions are capable of reaching equilibrium. Equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. And this has to be in a closed system. So the forward reaction is what we're used to. Reactants become products. However, products can become reactants. We've already discussed the fact that in order for a reaction to occur, first, the molecules must collide. Second, they must collide with enough energy to break the bonds. And third, they have to collide so that way they are oriented so that energy is actually focused at that weak point, at that bond. So if I have a molecule, okay, looks like this, let's say it's Cl2, and I have a hydrogen, which it also floats around as H2. If this hydrogen hits this point of this Cl, doesn't matter how much energy it has, it's not going to break the bond is up here. So the only way for H2 and Cl2, H2 plus Cl2 produces 2HCl, the way for this to occur is this point must collide with this point right here, both weak spots, so here and here. They need to collide with enough energy to overcome the bond they already have. So they must collide in the correct orientation and with the correct energy. This is how a chemical reaction occurs. Now what happens if I have an HCl and another HCl? Okay, so this reaction has occurred and I have product. Well, if these products collide with the correct orientation and the correct amount of energy, I can go back to producing reactants. That's what we call whenever we have a reaction going in a forward and a reverse direction. And if that rate of the forward, so producing this, equals the rate of the reverse going back and producing reactants, then we say it's at equilibrium, equal rates of production of products and reproduction of reactants. So when equilibrium is reached, it does not mean that the reactants and the products are of equal quantities. Okay, make sure we get this. They are not of equal quantities. So, equilibrium is going to be represented with a double arrow. You may also see it with a double arrow like this. Okay? So no matter what, we have an arrow pointing forward and an arrow pointing back because the reaction is occurring in both directions, going forward and back. So equilibrium is dynamic, which means it is constantly changing or fluctuating. Okay, so our equilibrium can change or fluctuate. Specifically, equilibrium means that my reactants and my products have constant concentrations. So it is equal rate, constant concentration. Those are the two concepts that are crucial for understanding this. Equal rate, so equal speeds of forward and reverse, constant concentration. That does not say equal concentration. We can have 1 drop of reactant and a lake full of product. But if the rate of producing that 1 drop is equal to the rate producing that lake, then it's still at equilibrium. Because we have a constant amount of 1 drop and a constant amount of a whole lake. Okay? So equal rate, constant concentration. So types of equilibrium. Now, all occur in a closed system. Don't forget this. If we have atoms leaving the system or coming into the system, that's going to change our equilibrium. But if we're in a closed system, so we're not gaining or losing atoms, then when we're talking about equilibrium, we're talking about the equal rates. So a physical equilibrium, we have two types of physical equilibrium. This is an equilibrium that involves physical changes. Our phase equilibrium occurs during a phase change. So this is when solid is going back and forth from a liquid, or a liquid is going back and forth from a gas. For these, I want you to assume, we have our diagram here. So if we're talking about a water, and we're talking at 0 degrees Celsius, so at this point, my rate of melting and my rate of freezing are equal. Just as many atoms that are in the process of turning into a liquid, we have an equal rate that's turning into a solid. Okay. Then my rate of evaporation equals my rate of condensation at that point. Okay. So all these concepts are always interrelated. The other type of physical equilibrium is solution equilibrium. This occurs at a solution's saturation point. So we're talking about a saturated solution. When we first discussed saturated solution, I showed you a picture of a beaker. In that beaker, we had a solution. We said it was at saturation. So all maximum amount of solutes that could be dissolved have been dissolved. If I were to add more crystals, then we had dissolving occurring here. But because we're at the saturation point, because the solution can no longer hold any more solute, then we also have at the bottom here crystallization. And these are equal rates. Okay. The speed at which we dissolve the solute up here is the same speed at which we produce crystal down here. Okay, because at a saturated point, all of these water molecules have separated everything as far as they can. They can't separate anymore. They can't take on any more solute. So when you added more solute up here, that created it so the water down here was no longer to hold the solute. If it can't hold the solutes apart from each other, they crystallize into the crystal. So this is yet another physical equilibrium. Equal rates here, equal rate of dissolving to equal rate of crystallization. A chemical equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. Or the rate of breaking bonds equals the rate of forming bonds. Now I hate how blurry this prints, but this is actually some really important information. So you might want to rewrite it in pen while we go over it. So I have my reaction rate on my Y, time on my X. When we start a reaction, we start with all reactant. So I'm going to start with a really high rate of the reaction if all that I have are reactants hitting reactants. It's going to occur very, very quickly. But as these reactants start hitting each other and hitting each other, they start getting used up in producing the product. The fewer reactants I have, the less often they can hit, the less often they can produce product. So over time, the reaction rate here is going to slow down just because there's fewer of the molecules that can possibly collide to produce product. Now, once I've started producing product, my product can collide. When the product collides into other product, we have the reverse process. So if this was A plus B makes C and D, once I've started making C and D, well, the C's and the D's can hit, producing A and B. So this reaction rate starts to increase because I start producing more product that's capable of colliding and producing this rate. When these two rates are equal is here. This is equilibrium. Just as often as my forward reaction is producing product, My reverse reaction is producing reactant. It's reproducing reactant. So Le Chatelier's principle. Le Chatelier is the principle explains how a system at equilibrium will respond to stress. I want you to think about your own life. Stress, something that agitates, messes with you. Okay, you're at equilibrium, everything's going good. Something happens and screws over your equilibrium. So a stress is any change in temperature, concentration, or pressure that's put upon a system. Well, we already talked about kinetics. These are the things that change rate. Equilibrium is equal rate, so if we change rate, we change equilibrium. So when a stress is added to a system at equilibrium, the system will shift in order to relieve that stress and reach a new equilibrium. So an increase in the rate of either the forward or the reverse reaction is called a shift. If we shift to the right, so if we say that we go towards products, that means we're producing more product. If this rate starts increasing, I go faster and faster and faster and faster towards the product, I'm going to be producing more product. However, if we say that something shifts to the left, then that means the rate of the reverse reaction increases. And we're going to favor the reactant because we're producing more and more and more and more reactant. These arrows right here are crucial visuals for this. So if we say we shift to the right, that means that the arrow that goes on top gets a lot bigger. The one going to those products, that's happening a lot more often. If we shift to the left, the arrow going to the reactants gets a lot bigger. That reverse reaction occurs a lot more often, so we're going to have a lot more reactant. So different types of stresses. First one we'll look at is concentration. So concentration changes, then our equilibrium will change, or it will shift when a reactant or product is added or taken away. Well, if we add something, if we add more reactant, well, now there's more reactants to collide, that reaction rate will obviously increase. There's more of them, collisions are going to happen more often, rate increases. However, if we take away the reactant, there's less of them, they're going to collide less often, and the rate will decrease. Very logical. So when the concentration of a reactant or product is increased, the reaction will shift away from the increase. So the phrase here is add away. And we're going to draw arrows to represent this as well. So for example 1, we have ammonia reacting with oxygen. It's exothermic. I have heat coming out at the end. If we add water to this system, which way is it going to shift? Well, I have water here. I'm adding it, so let's put an arrow above. So I'm going to increase it. Increase the concentration here. Add away. So we shift to the left. So if I'm shifting this way, if my reaction is occurring a lot more often, this direction to the left, then NH3 concentration is going to increase. Let's try another one. If we add O2, so now we're over here, I'm adding it, so let's draw an up arrow. If I add O2, the system will shift, add away, draw an arrow away from the O2. So it's going to shift towards the products. So I'm going to be producing more product than my concentration of NO will increase. So we shift to the right, and NO will increase. If we add H2O, which we already drew the arrow for here, add H2O, add away, arrow away, we'll shift to the left again. And the concentration of NO will decrease. We shifted away from the product. If I'm producing a lot more of this reactant, that means I'm using this up. So this will decrease. I'll leave the last one for you. So when the concentration of a reactant or product is decreased, the reaction will shift towards the side that has experienced the decrease. So this time we're going to do take towards. So I have this reaction here, the production of glucose. If we remove water, so I have water here, and I'm taking away, so let's put an arrow down. Take towards. So we have an arrow going towards it. The system will shift to the left, and C6H12O6, so over here, if we're shifting to the left, it's going to decrease. If we remove O2, so O2 is over here, take towards, then we will shift to the right, and the C6H12O6 will increase. Now we've shifted towards the glucose, so we're going to be producing more of it. By the way, this is how plants work. If they didn't release the oxygen that we need, that's why we kind of like the plants, they produce the oxygen for us. Every time they produce that oxygen, they release it out of the system. They release that oxygen out of the plant. By releasing the oxygen, it shifts this reaction toward producing more glucose. They don't really use the oxygen for much. So they release the oxygen out of their pores and such. By releasing that oxygen, that shifts the reaction towards producing more sugar, which is their food. They need to produce this as much and as quickly as they possibly can. So this is used in nature. So this is the add away, take towards, summarized here. We can use the same concept of add away, take towards for temperature. When temperature is our stress, it involves increasing or decreasing the heat. So notice we can use the words heat, energy, joules, or kilojoules when we're referring to the temperature. We're just referring to the energy, really. And these can be written in the equation as either reactants or products. If it is a product, it is exothermic because it is exiting. If it is a reactant, it is endothermic. It is entering. I hope you're noticing how often all of these concepts are interrelated. So when the temperature or heat is increased, the reaction will shift away from the heat. Add away. If we add heat, there already is the heat there, we go add away. No change here. Add away. Specifically from where the heat is, because that's our component in the reaction we care about. When temperature is decreased, the reaction will shift towards the heat. So take towards. If we take away heat, we take away energy, we lower the temperature, take towards. So if I have my examples here, heat is a product over here. If we add heat, add goes up, away. Which concentrations will decrease? Well, we're shifting away from the products, so the concentration of my products, NO and H2O, will decrease. Using those brackets are going to be really important when we're talking about concentration. So when we added heat here, we added energy. These molecules started colliding a lot more often. When they collided a lot more often, it produced more of this. By producing more of this, we used up this. That's why their concentrations went down. That's why these concentrations will go up. Concentration of NH3 and the concentration of O2. We shift towards the reactant, so we produce more of them. The last stress is pressure. Now, just like when we talked about kinetics and rates of reactions, pressure only affects gases. That doesn't change here. So pressure only affects gases. If there is no gas in the equation at all, a change in pressure won't change the equilibrium at all. So we're only talking about gases. If we increase the pressure, the reaction is going to shift to the side with the least number of gas molecules, or the least number of moles of gas. So what we need to specifically look at here is coefficients, right? Those will represent how many moles we have. So coefficients of any compound with that little g. If we decrease the pressure, the reaction is going to shift to the side with the greatest number of molecules, gas molecules. Okay, we'll think about it logically. If I increase the pressure on gas molecules, I'm going to push them closer and closer to one another. They'll collide more often. The reaction will occur to go away from wherever they are. If they're colliding, they're creating the reaction to go away from their side of the equation. If we decrease the pressure, we're spacing them out more. They're further and further apart from each other. If they're further apart, they'll collide less often. Therefore, that side of the reaction will occur less often. And note, if there is no gas molecules, or if it's the same number on both sides, then there's no effect, no shift. So I have this equation here. CO2 gas going to CO2 aqueous. If we increase the pressure, the concentration of which species will increase? Well, over here I have 1 mole of gas. Over here I have 0 moles of gas. So we increase the pressure. Well, these guys are going to hit each other more and more and more often. If they're hitting each other, my reaction is going to shift this direction. Therefore, the concentration of which will increase? CO2 aqueous. And what will decrease? Well, CO2 gas. They're hitting each other more often. They're being used up and creating the aqueous. Now, if we decrease the pressure, well, once again, pressure only affects this side. It only affects the side with the more molecules of gas. So if we decrease the pressure, these are spread out more. They're going to hit each other less often. So the forward reaction will occur less often. Therefore, the reverse reaction will occur more often comparatively. So if we decrease the pressure, then the concentration of CO2 gas will increase, and the concentration of CO2 aqueous will decrease. Finish through page 11 anything that we skipped.